Okay, welcome to another day, another lesson in geometry. This will be the last section of Chapter 3, Section 3.6. A couple of little theorems about perpendicular lines. And we will be using the distance formula in this section as well. So, proof theorems about perpendicular lines. Okay, alright. How do you find the distance between a point and a line? And the objective today will be students will be able to find the distance between a point and a line. Well, so let's review the distance formula. Whoops. Let me back that up a little bit. Okay. So the distance formula, in case you forgot it, it's equal to square root x2 minus x1. And then you take that quantity and you square it. And you add that to the quantity over here, y2 minus y1, and you square that one. Okay, so now what you need to do is put these numbers in here and do the arithmetic. So this is what we could call x1 and y1, and this could be x2 and y2. Okay, so you just need to put the numbers in here. So continuing, we get 5 minus 2. We square that. We add that to 7 minus 3, and we're going to square that. And then we just need to take the square root of all that business. Okay, well, so this portion here looks like 3. Then you square that, you're going to get 9. Okay. Alright, and then 7 minus 3, of course, is 4. And if you square that, you're going to get 16. Okay. And so 9 plus 16 is equal to the square root of 25. And of course, the square root of 25 is just simply 5. So the distance from this point, 2, 3 to 5, 7 is 5. Okay. Now, it might be worthwhile to look at the graph real quick just to see what we did. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So basically 2, 3 would be right about here, and 5, 7, 2, 4, 6, 5, 7 would be 1, 2, 3, 4, 5, 6, 7 would be over here or so. And what we found was this distance, that distance from here to here. Well, wasn't that nice? I sense all the delighted feelings in your heart already. Yeah, right. Okay, so you probably already learned the distance formula from Pythagorean's theorem or from algebra, one of those places. Probably should have seen it before. In any event, those are kind of the problems that we'll have to do later on in this study guide and also on the homework assignment as well. So that's a good little warm-up problem. Let's see, here's another little warm-up problem. Let's see, if the measure of DBC is 90 degrees, DBC, oh, so this is 90 degrees over here. Okay. If that's 90 degrees, by the way, that means it's a right angle, right? Alright. What is the measure ABD? Well, if you notice, there is a straight line here coming across this way. Okay. And it looks like to me there's two angles that form that straight line. So they are adjacent angles, which I remember, let's see, they're called a linear pair. Well, so I have a linear pair here, and I also remember a theorem a while back. It said linear pairs are always supplementary, and supplementary means that these two angles must add up to be 180. Well, so if this is 90 degrees, that means this one over here is 90 degrees. Oh, now by the way, that means it's a right angle also. Well, this idea also is a theorem that's going to be very similar to what we just did right here. So let's continue. Here's a new theorem. Theorem 3.8. It says that two lines intersect to form a linear pair of congruent angles. Then the lines are perpendicular. That's sort of like the warm-up problem we just did. Remember, in this case here, instead of saying that we have the right angles, we're going to say that the perpendicular. But what is perpendicular? When we say two lines are intersecting at right angles, if two lines are perpendicular, they form two right angles. Is what we're getting at also. And we're also, well, in this theorem, it's just saying that those two angles are congruent. Okay. So if two lines intersect to form a linear pair of congruent angles, alright, those are congruent, then the lines are perpendicular. Alright. Sounds good to me. Okay. Here's another one. Theorem 3.9. If two lines are perpendicular, then they intersect to form four right angles. And this seems like it's related to the previous theorem. Previous theorem says that you have perpendicular lines here if those two are congruent and you have a linear pair. This one, we have two lines that intersect, and we just found out from the warm-up problem that those two angles would add up to 90. Well, it shouldn't surprise you too much that those two angles on the bottom would also be 90. So that turns out to give us four angles that are 90. And so all four of these are going to be right angles. Okay, so not surprising. So let's try a problem. This section seems so hard so far. I don't know if I can do it. In the diagram at the right, AB is perpendicular to BC. What can we conclude about angles 1 and 2? Well, since they're perpendicular, since these lines are perpendicular, definition of perpendicular says we get a couple right angles. So I could say that, oh, and I can also say they're congruent, okay? Because there's a linear pair right here. Remember that first theorem we looked at says this is a linear pair? Alright, and so, well, I think what we could say is that angle 1, the measure of angle 1, is equal to the measure of angle 2, and it's equal to 90 degrees. I think that's what we could say. And we could say, therefore, that's the symbol for therefore, it's not a gang symbol. Therefore, we have two right angles. I think that's what we can conclude. Alright, easy enough, huh? Well, so let's see what they say. AB and B are perpendicular, so theorem 3.9, they form four right angles. So you conclude that they are right angles. Okay, sounds good. Okay, so now we have another theorem, 3.10. It says, okay, if two sides of two adjacent acute angles are perpendicular, then the angles are complementary. Okay, so remember that complementary here simply means that the two angles add up to be 90 degrees. Add to 90. Okay, they add up to be 90 degrees. So in other words, you could put a plus sign right here, and you could say equal 90. Alright, that's an easy theorem too. I mean, it's pretty easy stuff so far. So, let's see. Given that angle ABC is equal or congruent to ABD, what can we conclude about angles 3 and 4? Well, according to theorem 3.8 said, if this angle and this angle are congruent, then the lines are perpendicular, right? Or you have perpendicular here, so that means that's a right angle here, which means this side over here is 90 degrees. It means this side over here must be 90. So what it means then is that angles 3 and 4 must be complementary. So angle 3 and angle 4 are complementary. Angles, okay? Alright, so that's not too bad there. I mean, explain how do you know? Well, according to theorem 3.8, let's back up there. Okay, 3.8 said if two lines intersect to form a linear pair of congruent angles, then the lines are perpendicular. And then we found out from theorem 3.9, if the lines are perpendicular, then they're all right angles. So there you have it. And so we found out that, let's review it real quick. We found out first of all that this was 90 degrees, this was 90 degrees because they're congruent, and they're right angles, they're perpendicular. So it means a right angle there and a right angle there. And so since you have a right angle over here, it means it's 90 degrees, so we know that they're complementary. Well, so far it's kind of boring. Alright, so here's another theorem about perpendicular stuff. If a transversal is perpendicular to one of two parallel lines, then it's perpendicular to the other. So what it's saying is that, look, you have this fact first, okay, then you have this fact is second, okay. Now that's only the case if you have parallel lines, you see, and we have parallel lines. So if a transversal, now by transversal, remember it's a line that intersects two other lines at two different points. So we do have a transversal, that's what J is right here. If a transversal is perpendicular to one of two parallel lines, then it's perpendicular to the other one. Well, that seems obvious because they'd have to have the same slope, right? And if the slope here is a perpendicular slope, then the slopes here would have to be perpendicular. Well, that seems pretty obvious so far. Here's another theorem about perpendiculars. Let's see here. In a plane, if two lines are perpendicular to the same line, then they're parallel to each other. So what this one is basically, it's the converse. It says if you have this and this, okay, then you find out that these lines are parallel. Okay. By the way, we kind of know that also because look, there's a let's see why we know this real quick. It's pretty obvious. What kind of angles are these two? they're not complementary, they're corresponding, right? If you look at this is a transversal, right? And since that's a right angle, this angle here is congruent to this angle here, right? And we learned way earlier in chapter 3, section 3.4 or so, that if the corresponding angles are congruent, then the lines are parallel. So that's a pretty easy theorem to prove. I just proved it. Well, okay, let's keep rolling. I think we're getting up to the hardest portion of the chapter now. No, not yet. It's when we get to the distance portion. Okay, so determine which of the lines, if any, must be perpendicular. Okay. Oh, well, here's the corresponding angle idea. This angle here is congruent to this angle over here. And if you notice, we have a transversal. This line D is a transversal because it intersects two other lines. There's the two other lines, two different points. And according to section 3.4, if the corresponding angles are congruent, that means that this line here is parallel to this one. And we just learned from the previous theorem that if one of these lines is perpendicular and you have parallel lines, then so is the other one. So we're going to say that that's perpendicular. That's determine which of the other lines, if any, must be perpendicular. So we're going to say line A is perpendicular to this line over here, line C. Explain your reasoning. Well, it's because number one, we have, let me back that up. Let's write this out here a little bit. We have corresponding angles congruent, that are congruent, okay? So that's where we had right here. We had corresponding angles congruent. That then means that line A is parallel to line B. And once we have that, then we can say line A is perpendicular to line C because of theorem. There was a theorem, I think it was 3-11 or 3-10, that said if one of these is perpendicular, the other one must be perpendicular if you have parallel lines. So there you go, we have the explanation right here. Yay. Alright, well, B and C are perpendicular by corresponding angles. Okay, well, there you have it also. So you're going to have a couple tricky diagrams to deal with. And let's be careful here. We don't want to make assumptions when we have our diagrams. Is B parallel to A? Is line B parallel to A? Well, because of these two right angles, you have a transversal. This is a 90-degree angle, that's a 90-degree angle. And we have a theorem that says if you have one right angle, you're going to get four right angles in here. And if you have a right angle there, then this angle here is congruent to this angle here, right? And those are corresponding angles, so that means that these lines here are parallel. So, yes, we could say yes. Yes, because because corresponding, oh my goodness, who writes this bad anyways? Because the corresponding angles are congruent. Okay, let's just leave it at that. How about, is B perpendicular to C? Is this line? Well, yeah, we have that the lines are parallel already. We established that. And this one's perpendicular already. And there was that theorem that said, look, if one of these is perpendicular, then so is the other one. So, yes. Yes. Because we have parallel lines. Oh my goodness. Parallel lines. Well, maybe I should write it this way. And just say line A is parallel to B, then by theorem, I think it was 3-11 or 3-10, if you have one perpendicular angle, then the other one's perpendicular. So then by theorem 3-11, B is perpendicular to C. Oh my, this is tough stuff. Okay, so now we get to the distance stuff. Alright, the distance from a point to a line is the length. Oh man, I'm allergic to math. It's terrible. Okay, so the distance from a point to a line is the length of a perpendicular segment. It's always the length of a perpendicular segment. This perpendicular segment is the shortest distance. Okay, so what it's saying is that when we're talking about distance from a point to a line, we're going to go the shortest distance. In other words, we don't go from here to here and call that a distance. Okay, the distance is always going to be the shortest, and when you go the shortest, it's going to make a perpendicular. So you get always a right angle in there. Okay, so that's one of the things we're reading about here. Okay. What else are we thinking about? The distance between two parallel lines. How do we do that? Okay. The distance between two parallel lines is the length of any perpendicular segment joining the two. So you could use this one, or you can use this one, or you could use another one. As long as you have perpendicular, two perpendiculars there, you can join them together. Alright. Sounds good. Okay, whoop-de-doo. Alright, so let's take a look here at an application problem. Here we have a partial map of a town that's drawn on a graph where units are measured in feet. Okay. Line HL represents Main Street, so that's this street here. And CM represents 4th Avenue. Point L represents the library, C represents the center of town, H represents the high school, and M represents the medical center. Okay, so we're going to try some distance problems here. It says find the distance between the medical center to the high school. Okay. Click on my pen here. So the medical center, which is right here, to the high school right here. Well, this is a horizontal distance, so we're just looking for this distance here. And we can just count off the distance using this length here on this grid here that we have. Now this is just a straight horizontal distance. Now on our previous slide we said the distance from a point to a line always has to be perpendicular. but we're not finding the shortest distance in this case. The shortest distance would probably be right here somewhere because it'd make a perpendicular. So this obviously is not going to be the shortest distance to the line itself. But in any event, that's 100, that's 200, 300, 400, 500, 600, 700. So this total distance is 700. And the unit we were told was feet. So that's 700 feet. So that takes care of part A. How about part B? How far away is the medical center from the center of town along 4th Avenue? Alright, so we want to find out this distance. Well, to do that, we can just use our regular distance formula. Distance is equal to the square root. We did this like on our warm-up problem in the beginning of the class. It was x2 minus x1, and then you square that. Then you add that to y2 minus y1, and then you square that. And that's how we can find this distance. Just use those coordinates. Now, what we need then are the coordinates right here. The coordinates right there, it looks like to me the x coordinate would be 500. So it's going to be 500. And what's the y coordinate? The y coordinate right here is 600. And then we need the coordinates down here. The coordinates right here, the x coordinate is 900. Okay. And the y coordinate is 300. So we have our coordinates. Now let's just keep track here. If this is my x1, this is my y1, this is my x2, this is my y2, I just want to put the numbers in where they go here now. So according to my distance formula, I need to take this number and subtract that one. So let's see, that's going to be 900 minus 500. Okay, and then I'm going to square that. I'm going to add that to, well, this one minus that one. So 300 minus 600. And then we're going to square that. And then we have to take the square root of all that. Well, this looks like to me it's equal to 400 squared, which is going to be 1600. And that looks like to me it's going to be negative 300. But when you square that, you get 900. Okay? And then we take the square root of that. We get the square root of 2500, which of course is just simply equal to 500. So that distance from here to here is 500 feet. So now we did part B. Okay, so now let's just erase some stuff so I can do the next part here. Alright. Clean things up a little bit. How about if we do part C now? I'm going to use red for part C. What is the distance? What distance do you walk if you go from the medical center to the library? Medical center to the library. If you walk along 4th Avenue, so you got to go this way. Okay. And then you got to go that way. Okay. Well, we already found out that this distance is 500 feet. Okay, that's what we just did from part B. What we need to figure out now is the distance from here to here. Because what happens here, let's see, what is the distance to walk from the medical center to the library along 4th Avenue and Main Street? Round your answer to the nearest split. Okay, so we're going this way first, and then we're going that way. So That is the distance we need to find out now. So let's just repeat this process with this distance right here. So use my big eraser. Let's just restart this. Okay. So we're going to say it's equal to the square root. Alright, so we need some coordinates again. Well, the coordinates of this point, we said before, the x coordinate is 500 and the y coordinate is 600, right? And the coordinates up here at this point, okay, looks like to me the x coordinate is 700. So I'm going to write that right up here, 700. And the y coordinate looks like to me right up here is 800. Okay, so my distance formula, I need to take this one and subtract that one. So I get 700 minus 500, right? We could do that in our head, right? So well, I'll just write it out. Minus 500. And then we need to square that. Okay, and then we need to add that to this one, subtract this one. Well, it's going to be 800 minus 600. And then we need to square that. Well, if I did my math right, this is going to be 200. And then you square that. Well, 200 squared is 40,000. And 800 minus 600, that's another 200, so that's 40,000. $200 here. Let's see, 200 squared, 200 times 200. Yeah, that's going to be 4 zeros. Yep. And so then we take the square root of that. So what we find out, and probably I should use a calculator for this, is that's going to be the square root of like 80,000. What is the square root of 80,000? Let's see here. I get, this is approximately 282.8 feet. Now, we're supposed to go to the nearest foot, so we found out this distance was 500 feet, okay, and if we add on the 500 feet, okay, we're going to get 780. Let's see, we've got to round that to the nearest foot, so that's going to change this one to a 3. You see, round that to the nearest foot. So if we add these two together, then we're going to get 783 total feet. Alright, so we found part C. Wow, a lot of work, huh? Now, here's a question. So one of the things we might have been wondering, is this the shortest distance? Okay. Well, that's what part D is about. We're trying to figure out, this will turn out to be the shortest distance if those two lines are perpendicular. Remember, the shortest distance is always the perpendicular path. So let's check this out. Let's check this out. Part D. What we're going to do is find slope number 1 and compare it to slope number 2. Remember, if slope number 1 times slope number 2 is equal to -1, that would suggest that we have perpendicular lines. So slope number 1, once again we need to use the coordinates. So what are the coordinates of this point? We've had it before. It's I'm going to write it down here, 900 and 300. Okay. The coordinates for this point we've had before, it's 500, 600. Okay. So slope number 1 we'll find going this way. So it's got to be negative because it's going down, right? So remember, it's rise over run, so it's y2 minus y1 over x2 minus x1. So in this case we're going to subtract these coordinates. So 300 minus 600 over 900 minus 500. Okay, well in this case we get negative 300 over 400. And so I think you can knock off the zeros, and so this equals negative 3/4. So that's slope number 1. Okay, so let's get back to business. Now what we need to do is find the slope. Alright, we need to find the slope going the other way now. Alright, so what is the slope going this direction now? This slope. So we have the coordinates of this point, and once again we need the coordinates from this point. So that we said was 700 comma 800. Goes up there. Okay, so 700, 800. So slope number 2, remember it's rise over run, so we got to subtract the y coordinates. So it's going to be 800 minus 600 divided by 700 minus 500. And so this would give us 200 over 200, and that's equal to 1. And you'll notice these are not perpendicular then, because we'd have to have the reciprocal. Remember, we'd have to have 4 over 3. And remember, one of them has to be negative, one of them has to be positive. We don't have that as our slope. So what it means is that is 4th Avenue perpendicular to Main Street? The answer would be no. Because slope 1 and slope 2 are not negative reciprocals of each other. Or you could say slope number 1 times slope number 2 does not equal negative 1. So there you have it. Boy, these distance ones take a little bit of work. So those would be the hardest types of problems you might have on this assignment. So you have an example in your book as well that you could probably use. It's kind of a hokey problem, but anyhow, let's continue with the lesson and wrap things up. So how do you find the distance between a point and a line? For the coordinate plane, write an equation for the line through a given point and perpendicular to the given line. Find the point of the intersection. Use the distance formula to calculate the distance from a point to the... Well, that could be pretty tough work sometimes. So anyhow, that's the end.